This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Right. We discussed in detail in terms of how to improve the Rankine cycle. We discussed a few principles and as well as the practical ways to actually improving this cycle in terms of their thermal efficiency. Right. So one thing we discussed is called the reheating. And this process, if you're looking at the TS diagram, that's similar. It's a spike on the power section of that cycle. And we saw a similar feature previously in terms of the Brayton cycle reheating and the turbojet cycle after burning. So here, the reheating is being used again to add the energy during the process that the work is being delivered or useful output of the from the cycle is being delivered. So here, the major purpose of reheating is to raise the steam quality so that certain features that you can implement to improve the cycle efficiency. As we said, reheating itself is not necessarily increasing the efficiency of the cycle, of the Rankine cycle, but it enables some other process. For example, the high boiling, high pressure in the boiler, so that you solve the steam low quality steam problem, so that you can using the high boiler pressure, right? To enable, for example, higher boiler pressure to increase the efficiency. All right, so that's one practical modification of the basic Rankine cycle. Then another one we discussed called the regenerative Rankine cycle. And in this case, the idea is to not fully expand the steam, So direct a fraction of the partially expanded steam so that uses that steam which containing enthalpy and using that steam to heat the compressed water. So there is two ways we can do that. One is called open feed water heater, which we already discussed, and the other one is called closed feed water heater. So if we're looking at the schematic, we went through the open one, and you have the partially expanded steam, a fraction of it, and coming down here to heat the compressed water coming from the pump. So you're using a mixing chamber to achieve this process. So during the mixing process, the pressure of these two streams must come to be the same. And then this pressure is lower than the final boiler pressure. And the reason for that is you partially expand the steam, right? The steam is already partially expanded, which means the pressure there is lower compared to the boiler pressure. The boiler pressure is equal to the inlet pressure of the steam of the turbine, right? So you reduce some pressure, and then you pump a little bit to an intermediate pressure, then mix them. Then after they have the heat transfer or heat exchange, then have another pump to connect to go into the boiler. So in this case, you always need another pump because you're dealing with the intermediate pressure when you're mixing these two streams. And the other one is called closed feed water heater, which is shown here. So the only difference is in this case you do not mix them. You're using a heat exchanger so that the water flowing in its own path and the steam is flowing in its own path. So they don't have the pressure equilibrate with each other. So there is certain advantage between these two. Open case is simpler in terms of the setup and cheaper. The closed case is more expensive and more complicated, but it has own advantage in terms of it only requires one pump to pump the compressed water directly to the boiler pressure. It doesn't, unlike the open case, you always need an additional pump in order to reach the boiler pressure. So what we're going to do next is we are going to draw a TS diagram for the closed feed water case as well, just like we did for the open case. So I want to have this. All right, so showing here so that I can draw the TS diagram. All right, so if I started with the state 1 there, which is state 1 there, then I use one pump to directly pump the water to the boiler pressure. So I directly jump to this line, high pressure line, which is state 2, right? So I have the steam coming from the other stream. So let me draw that line. So it's starting from the state 6, 7, and 8. Right? So they will have heat transfer in this heat exchanger. the closed, so-called closed feed water heater, but that's basically a heat exchanger. So it's coming this way, and this one is coming this way. They are going up. And at the exit of the closed feed water heater, the state 9, which is for the compressed water. So if I have there, which is state 9, exit of the feed water heater for the water. And then for the steam, assume at the stage 3 it's a saturated liquid. So I'm right on that saturation line. And then this one needs to catch up in terms of pressure to the boiler pressure. So this one goes up again to the state 4. Right? And then you have, you want to mix them together because both are now water. You want to put in all the water into the generator, into the boiler. So they come together to have the state 5, which is the exit of this mixing chamber. Then that's inlet of the boiler. So the state 5, that's the inlet of the boiler. Then they're going to the state 6, and like this. All right, so we discussed that the mass fraction or mass flow on each of these process are not necessarily the same. So here, if we have the y fraction of the steam being directed into the feed water heater, and this line would be 1 minus y, and the top line would be 1. Right? So we can calculate the energy term and taking into account that this mass fraction. So in terms of the total work, we have 2 segments. So the partially expanded and the fully expanded. So that would be H6 minus H7 times a mass fraction of 1. So it's coming down here is 1. So here is a 1, here is a 1 minus y, right? And then you have the H7 minus H8 times 1 minus y. So that's your total turbine work, and your total pumping work would be 2 parts from 1 to 2. So V1 P2 over P1 times the fraction of 1 minus y. Yep. And then the other pumping work, which is V3 P4 minus P3, then times y. So the difference of these two is your net work output there. And the Q in is H6 minus which state? Looking at here, the 5 is the combined flow of the 9 and the 4. So the 5 is somewhere in the middle. So there, so that's H6 minus H5, and times the mass fraction of the combined, which is 1. All right. So then the efficiency just we wrote before, WT minus WP over Q in. So the TS diagram looks quite complicated, but if you understand how this process goes step by step, then it's, in terms of calculation, it's not difficult. You just need to go to the check with the property table that kind of force to find the right number for the calculation. Right? So that's basically the case that we discussed, that you can modify the Rankine cycle to make the process more thermally efficient in terms of the energy conversion. So reheating and regenerative Rankine cycles. So what I'm going to discuss next is other than modifying the basic Rankine cycle, you can combine the Rankine cycle or the steam power with other energy processes. And this process can give you better utilization of the energy. So that's also commonly used. All right. So combining one of them is to combine the steam power with a process called process heating. So process heating is a process which requires certain low-grade thermal energy as an input. For example, in a chemical plant, in oil refinery, or during the food processing, you require certain temperature. It doesn't need to be very, very hot, like 150 degree to 200 degrees C temperature, and you need a certain pressure to drive the steam to flow. So those kind of temperature can be coming from partially expanded steam. So you can combine these two processes together and make a better use, or make a overall more efficient use of the energy. So this one is considered the process heating require or uses low-grade thermal energy. It's not like a turbine, which is have a huge amount of mass that you need high pressure and high temperature as an inlet to drive the process to go. There are certain process that doesn't require this high quality thermal energy. So you can use partially expanded steam to achieve that process. And this actually has been commonly used, if you heard of a name called cogeneration, or cogen as a short name. Cogeneration, you generate two, you serve two purposes by one system, or more commonly called a combined heat and power, so or CHP. The process looks like this. So the process looks like this. So ignore this expansion valve first, all right? So you have a boiler and have turbine, and the partially expanded turbine going into this process heater. So basically, it's a heat rejection process. You're going through the heater to heat the other purpose that you want it to do, and then after that, the steam being condensed to water, and then going into the pump to the same pressure as that going through the condenser, and then going into the boiler. So to some extent, similar to the feed water heater that we just seen. So we have partially expanded process, but this is not being heat. It's not using to heat the water, but to using some being used for some other purpose. And the rest going through a typical Rankine cycle, going fully expand, then going through the condenser, and then going through the pump. All right. So this setup shown here actually is can satisfy a varying load. So by adjusting the fraction going to the process heater or going through the turbine, you can serve different heat demand. So if it's low, then most steam fully expand going through the turbine, right? If the heating load goes up, then you just direct more steam to this heater. And then if it's really high, then you just close the path to the condenser. So which means all the steam will be partially expanded, then going through the process heater, right? So in that case, the turbine is still doing some work. But for the extreme condition, where you can just bypass the turbine, so there's no any work being done by this process, you just have this boiler generate the high pressure steam, then going through this expansion valve. So in this case, the turbine is not being used, so drop the pressure to the temperature and the pressure that you require for the process heating. So in this case, you basically one heater going to to serve a one heating purpose, right? So that can serve for different heating demand. And this process, the efficiency, or shouldn't say efficiency, the effectiveness of this process is characterized by something called the utilization factor. So it's a pretty straightforward definition, similar to the efficiency, except here we don't really convert all the heat to work, right? So we don't define this as efficiency, but as a utilization factor. So this one is defined useful output versus the required input. Useful output, including the turbine work output and the heat for that process heating purpose, as well as the Q. Maybe I should use a lowercase q, and the Q of your input. So this process can achieve a utilization factor, which is combine the useful work and the process heating over the input as over 0.8. So which means 80% of energy can be used effectively. We don't call this as efficiency because this is not a heat engine. And if I ask you one question, why this process is so effective compared to a typical heat engine, which is like a theoretical value would be no more than 0.5 in terms of the heat converted to work. Why this process is more effective? This percentage is much higher. Say it again? That's one thought. If I looking at here, this is not our exhaust heat. In fact, this is a part of the heat not being used to do work. So it's not coming from the condenser. If you use the energy in the condenser, you can consider that's a waste heat. But that's the right direction of thinking. Any idea? That require you have a pretty deep understanding on the second law, or particularly the Carnot engine. So the Carnot engine is a device, or the heat engine is a device which converts chemical energy to thermal energy or heat, then using that heat to do work, right? The process which is very inefficient is a heat to work process, right? So if you have your total input coming in, you can reduce the fraction of the energy going through the heat to work process, then the process will automatically be more efficient. So because you reduce the step which has the lowest efficiency. So what's happening here is basically you all the heat fully, all the thermal energy fully going through the turbine. That amount of heat is being converted to work. That part of conversion has the lowest efficiency, right? So by directing some of for the process heating, you reduce the amount of heat that's being converted to work, right? So that's again related to the energy transfer from heat to work. That's inherently inefficient and is limited by the kernel efficiency. Actually, if you're looking at the regenerative cycle we're using here, that's a similar idea. You do not allow all the energy being converted to heat, then to drive the turbine. Partially expanded, which means you still got the unused enthalpy, directly using them as a heat source instead of a heat to produce work source. Right? So that's some like a more in-depth understanding there. All right, so that's one process where the steam power is being combined with the another process, and this combined CHP process is commonly used in practice. Another one is the steam power plus the gas turbine power. So in this process, actually, it can, I should say, this. If you're doing this, the process called combined cycle. If you have heard of this, the combined cycle is like a next generation of the gas turbine or the power generation technology. So often, because it's combined with gas turbine, you call it the combined cycle gas turbine or CCGT type of technology. And the idea here is to consider the gas turbine as the exit of the gas turbine, the exhaust gas still at a significant temperature, so it can be up to 500 degrees C or hotter. And if you consider what we discussed, the maximum temperature for the steam turbine or the boiler outlet is somewhere around 600 degrees C, right? So the idea is to using the gas turbine exhaust, which is at a significant temperature, 500 degrees C, as the heat source to generate steam. So combine these two, you're using the gas turbine exhaust, consider of including significant amount of enthalpy there to producing steam. So that's the idea there. And this process is very efficient, and the highest efficiency has been reached, which is, I should say around, is already over 60%. So this is a typical heat engine efficiency because we output work. The output work is coming from the gas turbine as well as the steam turbine. So output work divided by the input, which is only at the gas turbine, because the steam is generated by the gas turbine exhaust, right? So if you have the turbine work plus the gas turbine work plus steam turbine work divided by the input energy at the gas turbine, the efficiency is over 60%. So this is higher than any heat engine that has been that can achieve today. So that's the highest efficiency for heat engines. Maybe I should also write is to use GT exhaust to produce steam for the steam cycle. So if I show you one of the schematic there, so that's, you have the top loop is basically is a Brayton cycle, and it's more like a regenerative Brayton cycle, right? The regenerative Brayton cycle means there we discussed that you also use the enthalpy in the exhaust, but you use that one to heat the compressed air. But in this case, you're using that enthalpy to generate steam. So the lower loop is the steam cycle, which you have the pump pumping water into this heat exchanger, and basically that heat is being used to generate steam, and then going through the turbine and going through the condenser process. So in general, this you need a large gas turbine in order to drive a relatively small steam turbine. That's just because the available energy in the exhaust is not too high. But if you're building a very large gas turbine plant, and then you can use it to you can attach a reasonable size of steam turbine with it. All right, so this one is also being used, and the new generation of the power plant often using this type of technology. And in fact, we are going to do an example just on this type of cycle. All right, so this is the first example that you are going to see here. It's coming from one of the previous exam. All right, so it says that you have a power plant which is running on the combined cycle, and with a simple gas turbine cycle and a simple Rankine cycle. And to give you some conditions, the inlet condition of the gas turbine, the pressure ratio of the compressor, and the turbine inlet temperature, which is the highest temperature in the gas turbine cycle, 1100 C. And it said the compressor and the turbine are not 100% efficient. All right, so that's the gas turbine side. Then the two cycle is combined by a counterflow perfectly insulated heat exchanger. So that's the one we saw before. And the exhaust of the gas turbine is to heat the water to produce steam. And then it says the heat exchanger is the only heat source of the steam turbine, steam cycle. All right, so that's being explicitly stated there. And then the steam leaving the heat exchanger as a certain condition, 6 megapascal and 325 degrees C. So that's the condition as the inlet of the steam turbine. That's the highest temperature of the steam turbine, steam cycle. All right, and then it also said the gas turbine exhaust leaving at a certain condition, the saturated temperature of the produced steam. So it's the temperature needs to be found out as well. And the condenser is operated at a certain temperature, certain pressure. All right, you can see this certainly is a vacuum. 100 kPa is about one bar, right? 1 atmosphere pressure. So, and then the steam turbine also have certain efficiency, right? And then it says that assume that both cycles are ideal, and except we consider that the turbine and the compressor, they are not have 100% efficiency, and then there's some constants being given there. All right, so the problem is clear. We have a combined cycle, Brayton cycle on the top, and the Rankine cycle at the bottom, and there is some non-ideal condition, which is only the compressor and turbine is not 100% efficient. Right, so the problem is clear. Then the question asks three parts. One is draw the TS diagram. All right, so that can be done. And then ask you to determine the mass flow rate of the air, which is the air going through the gas turbine, to produce 100 megawatts of power. All right, so we will discuss how to think for that problem. And then the third one is determining the efficiency of the combined cycle. All right, so 2 points, 20 points, 3 points. You know which part is most require most effort. All right, so let me start here. So let's draw the schematic first, even though the problem is not asking you to do that. That's certainly helpful in terms of when we draw the TS diagram. So we have the basic Brayton cycle, right? So we know how to do that. Basic Brayton cycle, and the exhaust is being used for some purpose. So let's put the heat exchanger there. So let's say this is 1, 2, 3, 4, and 5. All right, so that's the top loop. The bottom is the Rankine cycle. So we know that we draw starting from the pump, and the pump to the high pressure, then going in this heat exchanger, and then going through the steam turbine, and then going through a condenser to complete our simple Rankine cycle. So let's say start from there. If this 6, 7, 8, and 9. All right. The problem asks you to draw the TS diagram of the two cycles on separate plots. So let's draw the Brayton cycle first. So we have the 1, 2, 3, and 4. Except, sorry, it's not, should be vertical. Except now we need to consider that the compressor and the gas turbine, none of them are 100% efficient. So we need to consider that isentropic efficiency. So that will be more like this way. So if that's 2S, 2A, that will be 4A and then 4S there. And we have the state which going through this heat exchanger. We don't know where it is, so just put it as 5 for now. And then the Rankine cycle. Right, so we have the starting from the inlet of the pump, state 6, then going through the 7, and then going through 8 and 9. I didn't draw this very accurately. The slope here, actually, in the liquid side should be a lot more steeper than what I draw there, actually. So this state 6 and state 7 are not very far away. The distance of them is related to the work of the for the pump. So I didn't draw it very accurately. And anyway, so again, the steam turbine is not 100% efficient. So we need to deal with a case which a little bit tilted to the left, to the right. So if that's the 9A, and that's your 9S. All right, so that's the step. Let's basically set up the problem. And let's put down the knowns or given conditions there as well. So if we have what is given is T1 that is equals to, maybe I just draw here. So the T1 equals 20 degrees C. I directly convert it to the Kelvin because the calculation I used could involving isentropic law or the ideal gas law. So they're all using the temperature in terms of Kelvin. Do not using Celsius. Using Celsius must give you the number which is way incorrect, right? And the pressure, P1 is the 101 kPa, and the pressure ratio is 8. That is given as part of it. And the T3 equals to 1373 Kelvin. All right, and then what else? Then the turbine, the steam turbine, we have the T8 equals to the 325 degrees Celsius, and the pressure 8 is 6 megapascal. And the condenser, which is a P9, is a 20 kPa. Yep, that's everything. I don't really need to convert this to Kelvin because there I know I'm going to just go to the property table to find things. I'm not dealing with ideal gas, so it doesn't need to be Kelvin. And then we have the efficiency, right? The efficiency of the compressor is what? 85. Efficiency of the gas turbine is 0.9, and the efficiency of the steam turbine is also 0.9. All right, so I just put all these conditions together as a start. So by doing that, we actually complete the first part, which is requiring us to draw the TS diagram. So that part's done. And the second part, asking us to determine the air flow rate for a given power output of this combined cycle. Right, how do we, let's say the Q2, how do we think about this? So the energy term we dealt with so far is all work, mass-specific work. No matter it's turbine or compressor or the steam turbine or gas turbine, what we deal with is all work, right? And this mass-specific work, in terms of dimension, that's joule per kilogram of the working fluid, the mass-specific per kilogram of your working fluid. If it's gas turbine, it's per kilogram of air, steam turbine per kilogram of steam, right? Power is a different concept, right? The power has a joule per second dimension. So the output of power directly related to the output work. So that can be converted in terms of the mass-specific work times the mass of your working fluid, total mass of your working fluid, and then divided by time. So then this one is a kilogram, this one is a second, then you can get this value, right? And then you combine this mass versus time, that you would have the net work times the mass flow rate of your working fluid. All right, so that's maybe I said too much. That's something should be able to figure out if you understand the process. But here we have two cycle, which means the work that are coming from the gas turbine cycle is 2 times the mass flow rate of the working fluid of the gas turbine cycle, which is air. And then we have the steam turbine output, this 2 times the mass flow rate of the working fluid there, which is a steam. All right. So this kind of relationship, if we don't show this example, we will not discuss this in the subject. But there is nothing new. If you consider what the process is and how this work is being produced, how the power is being produced, that's the equation you should come up with yourself during the exam. All right. So it's a simple energy balance or the energy to power conversion. So this is something you need to come up with. I'm showing here just because we are doing this example. All right, so there are 2 energy terms, the gas turbine work, steam turbine work, and then that's something we can figure out based on our knowledge of the cycle we have studied. And then we need to figure out what are the this one is what is the problem we are asking, and then we need to figure out the relation between the steam turbine, steam flow rate versus the air flow rate. All right, so let's do the simple stuff, how to figure out these 2 work. So this is more of a routine calculation for these 2 basic cycles. So I will go through them relatively quickly. The only tricky point is you need to consider there is certain efficiency there. All right? So let me so just put it here so that we have something to look at when we do the calculation. All right, so let's look at the gas turbine cycle first. So for the GT, we know that we know the inlet temperature. So we directly after the work term, because the question is asking the work term. So let's figure out the work term, and if anything required later on in the following on calculation, let's do that later on. Let's figure out the work term first. So the first one would be determining the compressor work, right? So if we have the T1, which is equals to the 293, and the P1, which equals to 1.1 kPa. We want to know what is T2, because the compressor work is directly related to the temperature difference between the two states. So the T2 can be calculated from T2 over T1 equals to the isentropic relation. But I don't even need the isentropic relation because I know the pressure ratio is given to the gamma minus 1. So the RP is 8 and the gamma is 1.4, right? So by doing that, I can calculate the T2, which is 531 Kelvin. So this is isentropic process, and we said this the compressor is not 100% efficient isentropically, so this one will equals to 2s, right? And 2s, then we'll we need to figure out 2a, the actual state going through the compressor. Then the compressor efficiency can be written as a T2s T1 T2a T1, which equals to 0.85, which can readily find the T2a, that is equals to 573 Kelvin. All right, then we can determine the compressor work, which is Cp T2a minus T1. I don't have this number calculated here, so I just leave the equation there, and then later on we can bring all the numbers together. So that's compressor work, and then we want to find the turbine work. Turbine work, that's easy, 3 to 4a, right? So we can do the similar thing in terms of the T3 over T4s equals to RP gamma minus 1. Then we can quickly find the T4s 758 Kelvin, and bring the similar idea, which is turbine efficiency. The gas turbine efficiency would be T3 minus T4s, T3 minus T4a, 0.9. Then T4a would be 820 Kelvin. Then the net work from the gas turbine equals to the turbine work Cp T3 minus T4a minus Cp T2a minus T1. And the Cp is given, and then you will have the value of 275 kilojoule per kilogram of working fluid, which is air. Yeah. All right, I have to stop here. Let's continue tomorrow. Sorry.
T3 minus T4a divided by T3 minus T4s.
Yep. Yeah. Yeah. Just